Imagine something ticking. Not a clock powered by, batteries or springs, but something more fundamental.
Like a piece of matter itself.
Exactly. A piece of matter that oscillates all on its own. It's very structure pulsing in time. Sounds like pure science fiction, right?
It definitely does. Like something that shouldn't really be possible based on our everyday experience.
Well, get ready to have your understanding of reality maybe tweaked a little bit.
Okay.
Because that's the realm of time crystals.
Yeah.
They're a newly discovered phase of matter, apparently, that possesses a periodic structure. Not just in space, like, a regular crystal.
Right, like salt or a diamond.
But in time itself.
Yeah.
I'm Edward, and welcome to Dispelling.
And I'm Lily.
So on this deep dive, we're really plunging into a concept that, honestly, sounds like it's been ripped straight from a sci-fi novel.
Time crystals.
Time crystals. What exactly are they? Why is the physics world getting so excited about them? And maybe the biggest question, are they actually real?
That's the kicker, isn't it?
It really is. We've gathered a whole stack of cutting-edge theoretical papers, plus the results from some pretty groundbreaking experiments to explore today.
So we're looking at both the theory and the actual lab results. It's quite a journey to the edge of what we understand about matter and time.
Absolutely. Now, before we dive in, if you're finding these explorations into the weird and wonderful corners of science interesting, definitely hit that like button.
Please do. And subscribe so you don't miss what we tackle next.
Yeah, and check out www.dansplain.xyz. We've got the latest episodes there, plus articles, some partner products we like, and just generally more stuff for the curious mind.
Okay, so time crystals. Where do we start?
Okay, let's unpack this. To really get our heads around time crystals, we need to start with a concept that might seem a bit abstract at first. Symmetry.
Right. Symmetry is, it's fundamental in physics, isn't it? Think about a perfect sphere.
Yeah.
You can rotate it any way you like, and it still looks exactly the same. That's rotational symmetry.
Okay, got it. So now think about a regular crystal, like you said, salt or diamond. What symmetry is being broken there?
Well, in that case, it's the symmetry of space itself. Think about empty space. It's completely uniform, right? Looks the same everywhere in every direction. But a crystal, it imposes this repeating structure of atoms. So you look here, then you move just the right distance, and boom, you see the exact same arrangement.
So it's not uniform anymore. It has this pattern. It repeats, but only at specific intervals.
Exactly. It breaks that sameness of empty space. It has discrete spatial symmetry instead of continuous.
Okay, so that's breaking spatial symmetry. Now, the really wild idea with time crystals is breaking a totally different kind of symmetry. Time translation symmetry.
Yeah, and this one feels a bit weirder, maybe. Time translation symmetry is basically the idea that the laws of physics don't change over time.
Meaning an experiment I do today should work the same way if I do it tomorrow, assuming all conditions are identical.
Precisely. The fundamental rules are constant. That's time translation symmetry.
Right. So if a system has that symmetry, its basic behavior shouldn't depend on when you look at it. But a time crystal, it messes with that.
It does. It spontaneously oscillates or flips between states or pulses with a regular rhythm. But, and this is the key part, it does this without needing a continuous external push for each specific oscillation.
Whoa, okay, hang on.
It has an inherent rhythm in time built into its lowest energy state under certain conditions.
Doesn't that sound like perpetual motion?
Yes.
Does that violate energy conservation?
Yeah.
We're always told that's impossible.
That was the big question. And yeah, it caused a lot of initial skepticism. It sounds like you're getting something for nothing.
Right.
The crucial insight, the resolution, is that these time crystals, at least the ones we've made so far, exist in systems that are driven out of equilibrium.
Okay. Driven out of equilibrium. Let's unpack that a bit more. What does that actually mean in practice?
Think about a kid on a swing set. To get them going, you give a big push, right? Initial energy. Now, to keep them swinging steadily, you don't need a massive push every time, just small, regular nudges to counteract friction and air resistance.
Okay.
The swing's regular back and forth motion isn't directly powered by each tiny nudge once it's got its rhythm. The nudges just maintain the overall energy of the swinging system, keeping it going against losses.
I see. So the nudges keep the conditions right for swinging, but the swinging itself has its own natural period.
Kind of like that, yeah. With time crystals, there's an external driving force, maybe a laser, maybe microwaves, that continuously pumps energy into the overall system. It keeps the system in an energized, non-equilibrium state.
And within that energized state, The time crystal can then form and start its own slower oscillation.
Exactly. The energy input sustains the necessary environment, but the crystal's ticking isn't directly tied one-to-one with the energy input pulses. It finds its own inherent rhythm.
Okay, it makes a critical difference. It's not creating energy, it's organizing itself in time because of the energy being supplied to the whole system.
Precisely. So it sidesteps the perpetual motion machine problem.
Got it. Now, who first even dared to imagine such a bizarre thing? This feels really out there.
It was the physicist Frank Wilczek. He's a Nobel laureate. He proposed the basic concept back in 2012.
A Nobel laureate thinking about this stuff.
Yeah.
Okay, that definitely makes you take it seriously. What was his initial angle?
His thinking was sort of analogous to spatial crystals. He thought, well, if systems can spontaneously break the symmetry of space to form regular crystals, maybe they could also spontaneously break the symmetry of time.
Creating these time-periodic states.
Exactly. He initially imagined it might happen in systems already known for weird quantum behavior, like superconductors or superfluids, perhaps even in their ground state.
And what was the reaction from other physicists? I bet there were some raised eyebrows.
Oh, definitely. There was significant skepticism, mostly because of that energy conservation concern we just talked about. How could something oscillate forever in its lowest energy state? That seemed to violate fundamental principles of thermodynamics for systems in equilibrium.
But the breakthrough, as you said, was realizing they happen in these driven, non-equilibrium systems. How did that change the picture?
It changed everything. The external driving force continuously puts energy into the system, keeping it away from thermal equilibrium. In this energized state, the system doesn't have to be in its absolute lowest energy state overall.
So it can find a stable, oscillating state that is low energy relative to other possible states within that driven environment.
You've got it. The drive energy maintains the conditions, and within those conditions, the time crystal oscillation emerges as a stable pattern. The oscillation doesn't need a specific energy kick for each cycle. The background drive takes care of the energy budget.
Okay, I think I'm getting it. It's subtle but crucial. So how do scientists actually, make these things and see them? What are we talking about in the lab?
Right. Here's where it gets really interesting, because we have to go into the quantum world.
Always the quantum world with the weird stuff.
Isn't it just? So time crystals are typically made in quantum systems, like a collection of atoms or specific defects in a material that are periodically driven.
Driven how?
Usually with external forces, like carefully timed laser pulses or microwave signals.
The quantum systems, tiny scales, and then you're sort of poking them rhythmically from the outside.
That's a good way to put it. And this rhythmic poking, the external drive, has its own frequency. But the magic happens because the quantum system doesn't just follow along perfectly.
It doesn't.
No. This leads to what's called discrete time translation symmetry breaking.
Okay, discrete time translation symmetry breaking. That sounds technical. Break it down.
Imagine you're flashing a laser at the system once every second, so the drive period is 1 second.
Right.
A discrete time crystal formed in that system might then only change its state or oscillate every 2 seconds, or maybe every 3 seconds. Its response frequency is a subharmonic, a fraction of the driving frequency.
Huh. So the system isn't keeping up with the drive. It's like it decides, nope, I'm only going to react to every second flash or every third flash.
Exactly. Instead of changing with every single tick of the external driver, it sets its own slower pace. It only changes on every other tick, or every third tick, or some other multiple.
It's like it has a longer memory or slower internal clock compared to the thing pushing it.
That's a great analogy. And that's the key signature they look for in experiments. Does the system's behavior repeat at an interval that is longer than the period of the driving force? If yes, you might have a time crystal.
You keep saying discrete time crystals. Are there other kinds, like continuous ones?
Theoretically, yes. A continuous time crystal would oscillate all on its own, without needing that periodic drive, perhaps in its true ground state as Wilczek originally imagined. But proving that's possible without violating known physics laws has been really tricky, and experimentally, almost all the confirmed time crystals are the discrete, driven kind.
So the driven ones are the ones we know are real and can make.
For now, yes. They are much more accessible in the lab.
Okay, fascinating. It's this dance between the external rhythm and the system's own quantum nature. So who are the key players in actually making this happen? You mentioned Wilczek's theory.
Right. Wilczek laid the theoretical groundwork in 2012, but The first real experimental confirmations didn't come until 2017. A big moment was Christopher Monroe's group at the University of Maryland.
What did they manage to do?
They worked with a chain of deuterium ions. These are charged atoms trapped using electric and magnetic fields.
Okay, ions in a trap.
And they hit them with periodic laser pulses. What they saw was amazing. The spins of these ions started flipping back and forth, but at exactly half the frequency of the laser pulses.
Half the frequency. So exactly that subharmonic response you mentioned.
Precisely. Tick-tock went the laser, but the ions only went tick-tock. It was textbook discrete time crystal behavior.
Wow. Seeing that must have been incredible. Direct proof.
Absolutely a landmark moment. And crucially, they showed this oscillation was stable. Even if they nudged the system slightly, it would settle back into that half-frequency rhythm. That stability, that robustness is a key characteristic.
Okay, so that was one major confirmation.
And incredibly, almost simultaneously in 2017, another group reported success in a completely different system.
No way. Who was that?
Mikhail Lukin's group over at Harvard, they weren't using trapped ions, they were using diamonds.
Diamonds, like actual diamonds.
Well, specifically tiny imperfections within diamonds called nitrogen vacancy centers, or NV centers. These little defects have quantum spin properties, kind of like tiny magnets.
Ah, I've heard of those. They're used in quantum sensing sometimes.
Exactly. So Lukin's team used microwave pulses to drive these NV centers, getting them to interact. And guess what they saw?
Let me guess. Oscillations at a frequency lower than the microwaves.
You got it. They observed oscillations at a fraction of the driving microwave frequency. So, totally different systems, solid-state defects versus trapped ions, but the same fundamental time crystal behavior.
Two independent confirmations in different systems in the same year. That's really solid evidence.
It really cemented the idea that this wasn't just a fluke in one specific setup. But we should also mention another key theorist here, Norman Yau.
Okay, what was his contribution?
Yau, at UC Berkeley, published a crucial theoretical paper in 2016, just before those experiments. He basically provided a detailed theoretical framework and essentially a blueprint or a recipe book for how you would actually build and detect a discrete time crystal in these driven quantum systems.
Ah, so he sort of paved the way for the experimentalists. Showed them what to look for and how to build it.
Absolutely. His work was incredibly influential in guiding Monroe's and Lukin's groups and others that followed.
So Yau provided the map, and Monroe and Lukin got there first.
A good way to summarize it. And the research didn't stop there. In 2021, there was another interesting development from Andreas Hemmerich's group in Hamburg.
What did they find?
They managed to create something called a dissipative time crystal.
Dissipative? What does that mean?
Most of the early experiments tried to keep their quantum systems really isolated from the outside environment to preserve the delicate quantum effects. Hemmerich's experiment was in an open quantum system, one that naturally loses energy to its surroundings. It dissipates energy.
And they still saw time crystal behavior, even with energy leaking out.
Yes. It showed that these time crystals aren't just confined to perfectly isolated closed systems. They can emerge even when there's interaction and energy exchange with the environment, which actually broadens the possibilities of where we might find them or how we might use them.
That seems important. It suggests maybe they're not quite as fragile or exotic as initially thought.
It certainly expands the scope, yes.
Okay, so theory from Wilczek and Yau, landmark experiments from Monroe and Lukin, refinements like the dissipative ones from Hemmerich. It really sounds like the answer to our big question, are they real, is a resounding yes.
Absolutely yes. At the quantum level, under the right laboratory conditions, time crystals have been repeatedly created and observed. It's moved beyond pure theory.
Let's just quickly recap the evidence trail then. We have Monroe's trapped ytterbium ions oscillating at half the laser frequency.
Check. Lukin's diamond NV centers doing the same with microwaves.
Check. Then there was that 2019 experiment using ultra-cold atoms bouncing on an oscillating mirror, showing it works in yet another setup.
Yep, demonstrating versatility. And observations have also been reported in nuclear magnetic resonance NMR systems using complex organic molecules.
NMR, like in medical imaging, but applied differently here.
And even more recently, wasn't there something with semiconductors?
Yeah. 2025, researchers at TU Dortmund University. They observed time crystal dynamics in indium gallium arsenide. That's a common semiconductor material.
And didn't they see some complex stuff happening there too?
They did. They reported observing not just the basic time crystal oscillation, but also more complex nonlinear behavior, including transitions towards chaos. It suggests there's a lot of rich physics hidden in these systems.
So the evidence is broad now. Ions, defects, atoms, molecules, semiconductors, all showing this characteristic subharmonic response to a drive.
The conclusion seems inescapable. Time crystals are real, quantum phenomena, achievable in labs.
Definitely. But now we need to be really clear about what that means, and maybe more importantly, what it doesn't mean, because the name itself can be a bit misleading.
Good point. Time crystal and oscillation without energy input per cycle still sounds suspiciously like free energy or perpetual motion to the casual ear.
Exactly. So first things first. These are not macroscopic objects like a quartz crystal you can hold. You won't trip over a time crystal in the street. They are quantum phenomena existing at the scale of atoms and their interactions.
Right. They live in the quantum realm under very specific conditions.
And second, the crucial point we discussed. They do not violate energy conservation. They don't give you unlimited free energy.
Because they are driven systems.
Yes. The oscillation, that seemingly perpetual motion, is sustained by the energy continuously supplied by the external drive, the laser, the microwaves, whatever it is. The energy has to come from somewhere to keep the system out of equilibrium.
So no free lunch, the energy input maintains the overall state, and the crystal just organizes itself periodically within that state.
Perfectly put. It's not about creating energy. It's about a novel way matter can organize itself in time when energized.
It's a new phase of matter, but obeying the known laws of physics.
Exactly. A new, non-equilibrium phase of matter.
Okay, so they're real, they're quantum, they don't break fundamental laws.
Yeah.
Got it. So why should we care? Why is this discovery considered so important? What are the big implications?
So what does this all mean? Well, the implications could be pretty far-reaching, actually, touching both fundamental science and potentially future tech.
Let's start with the fundamentals. You mentioned they challenge traditional thermodynamics.
They do. Thermodynamics, especially equilibrium thermodynamics, often tells us that systems tend towards disorder, towards maximum entropy, especially if you're pumping energy in. Things tend to just heat up randomly.
Right. Things tend to get messy.
But time crystals show that even in these constantly driven, non-equilibrium systems, you can get spontaneous emergence of order, stable, coherent, periodic order in time. That's unexpected.
So they show order can persist where we might have expected chaos.
Precisely. And understanding how order emerges and stabilizes in driven systems is crucial for, well, almost everything complex, from biological cells processing energy to potentially even cosmological models. Time crystals give us a clean, fundamental example of this non-equilibrium order.
That's a really profound shift in thinking. Okay, what about the tech side? You hear whispers about quantum computing.
Yes, that's definitely one of the most exciting, though still speculative, potential applications. The idea is that the inherent stability and periodicity of a time crystal could make it a great candidate for quantum memory.
Quantum memory?
Yeah.
Like storing the quantum bits, the qubits, for a quantum computer.
Exactly. One of the biggest headaches in building quantum computers is decoherence. The qubits lose their fragile quantum states really easily due to noise from the environment.
They're very delicate.
Extremely. But a time crystal's oscillation is intrinsically stable and robust against small perturbations. That's part of its definition. So the hope is you could encode quantum information in the stable state of a time crystal, and it would be much better protected against errors.
That could be huge. Like a more robust way to build the core components of a quantum computer.
It could potentially improve reliability and allow for longer, more complex quantum computations. It's a very active area of research.
Okay, quantum memory. What else? Any other potential gadgets?
Well, think about their stable oscillations again. Anything that oscillates very regularly and predictably can potentially be used for measuring time or sensing changes.
Ah, like making better clocks or sensors.
Exactly. Because the oscillation frequency is so stable and can be very sensitive to external fields or conditions, time crystals might one day lead to ultra-precise clocks or sensors.
Better than atomic clocks. Those are already insanely accurate.
That's the ultimate dream for some researchers. Whether they can actually surpass the best atomic clocks remains to be seen, but the potential for highly stable frequency standards is there. Imagine GPS navigation with pinpoint accuracy, faster communication networks, or even new tools for testing fundamental physics.
Wow. Okay, so quantum computing, super clocks, ultra-sensitive sensors. The potential list is impressive. And what about the really big picture stuff, the nature of time itself?
Yeah, on a more philosophical level, the very fact that time translation symmetry can be broken is thought-provoking. It suggests that time, maybe like space, isn't just a smooth, uniform background.
But it can have structure, or periodicity, under the right quantum conditions.
Kind of. It hints that at the quantum level, time might behave in ways we haven't fully appreciated. This could potentially connect to really deep questions in physics, maybe even offering clues for theories like quantum gravity that try to merge quantum mechanics and general relativity.
That is seriously mind-bending. Time having structure.
Okay.
This all sounds amazing. But let's bring it back down to earth a bit. What are the catches? What's stopping us from having time crystal clocks on our wrists tomorrow?
Right, reality check time. It's crucial to remember this is still very early stage research. Practical applications are largely speculative at this point.
So lots of hurdles still.
Oh, absolutely. First off, scalability is a massive challenge. We're talking about creating and controlling these things often with just a handful of atoms or ions, usually at extremely low temperatures, using complex laser setups.
Not exactly something you can mass produce easily.
Not yet, certainly not. Figuring out how to build larger, more robust time crystal systems, and then how to integrate them into any kind of practical device is a huge engineering and physics problem.
So seeing, say, a time crystal-based quantum computer or commercial sensor is probably not imminent.
Definitely not imminent. We might be talking years, more likely decades, before we see tangible benefits outside of fundamental science labs, if ever, for some of the more ambitious ideas.
Okay, so excitement is warranted, but patience is required.
That sums it up perfectly.
Yeah.
The fundamental discovery is incredible, but the path to application is long and uncertain.
Still, even without immediate gadgets, discovering a whole new way matter can behave, a new phase of matter.
Yeah.
That's a huge deal in itself.
It truly is. It fundamentally expands our understanding of the possibilities within the laws of physics.
Okay, so let's try to wrap up this deep dive. The big takeaway: time crystals are real. They've been made, they've been measured.
Yep, experimentally verified. They represent a new phase of matter, one that breaks time translation symmetry.
They oscillate periodically, but not because each oscillation is directly powered. It's an emergent property within a system that's being constantly driven out of equilibrium.
Exactly. They live in the quantum world in these driven systems, and they don't violate energy conservation.
And the potential implications are tantalizing, maybe more stable quantum computers, incredibly precise clocks and sensors.
And maybe even new insights into the fundamental nature of time and non-equilibrium physics itself.
But we need to keep our feet on the ground. The practical applications are still a long way off, facing significant scientific and engineering challenges.
Definitely. Early days, lots more research needed.
So here's a final thought to leave our listeners with. If matter can have structure in time, just like it does in space, what else are we missing?
Right. Does this fundamentally change how we should think about the universe, about reality, and all the possibilities hidden within it? What other symmetries might be broken in ways we haven't conceived of yet?
It really opens up the imagination, doesn't it? Makes you wonder what other strange phases of matter or reality are out there waiting to be discovered.
It's why fundamental science is so endlessly fascinating. You poke at the edges, and sometimes you find something completely unexpected.
Well, thank you for joining us on this journey into this seriously weird and wonderful world of time crystals. It's been mind-bending.
My pleasure. It's a topic that's definitely going to keep physicists busy for a long time to come.